Yes, so my presentation will be about, I've been working on that subject with many people, including some participants in the room. And the outline of our presentation is the following. I will start more like with an introductory tutorial presentation of this technique, the basics. I will go back to some basics. And then I will describe what have been provided, what interesting tools have been provided to study this technique, which are modern random access technique. And then I will more focus on recent results or future work that we are interested in, like making this technique more realistic or using a dual tech. So in introduction, so we are back to the classical system of massive machine type communication, a lot of devices. A few of them are active and some few packets. So as you know, in this setting, the signaling can become huge, and one way is NOMA. So there have been presentations. Marceau presented some NOMA technique. And I go back still to the basics. So if you have a non-orthogonal multiple access, then by definition you will have simultaneous transmission on some part of a spectrum in time and frequency. And then you can do what Marceau indicated. You can do something like first, like successive interference. I go slowly. So you assume, for instance, that you have two users, A and B, they transmit at the same time on the same resource. And you have one user, maybe which is transmitted, you have power imbalance, so one user is transmitting with much higher power, and then you can use a normal decoder to recover the packet. So then when you do that, you can reconstruct the signal of the user that you have decoded. Here it's A, and you can physically subtract the signal that you have reconstructed to the initial signal that you received, and you get something, if you did everything well, which is a little bit what B sent, and then you can recover B. So this is a successive interference constellation. I'm explaining this because, okay, there is a lot of technique around that, but I'm explaining this because you can use this technique from another point of view. So myself, I'm more from network and distributed system background. So I started telecommunication with random access. So in random access, you have this simplified model, ideal model, where, okay, the time is divided in slots. So this is another terminology for resource element, resource block. It's simplified, so it's only one channel, and you can transmit one packet in a slot. So this is still textbook, and then when two users transmit at the same time, the collision, and if one user transmits alone, so this is my layer. So by definition, every time you have symmetric transmission, you will lose one slot, and you will never use the information because of a collision, and then you are limited in the throughput. You cannot do the bound, of course, here is one packet per slot, but you do much less than that. You do maximum almost half of it, a little bit than half is a bound. So now you can go back to revisit random access with the SIG that I just represented. So now you look a little bit differently. You assume, for instance, that you have two simultaneous transmission on the first slot, so A and B. So this is a collision for people doing random access. We're transmitting the packet. So now you can do something as before. You can reconstruct actually the signal of A, and then you can put superposition here. Here you don't necessarily have a power imbalance, it's something to notice. And then you can again try to remove the signal from A from this slot and get something which is hopefully like the signal of B and recover B. So the the thing that should be noticed here is that it's different from classical SIC, because you subtract the message of a recover on another resource element, let's say, and then you need to estimate the parameter. Whereas if you do normal seek, you will get more or less implicitly when you recover message. So this is a basic building blocks. So this mixes a physical layer and a MAC. And then you can construct protocol on top of that. So one early work that did so is a work on satellite communication. So you have this classical random access settings. So you have a frame, again with slots, you have user. Here you can have user that transmit on one slot, so it's LOI, you know. You can do diversity sorted LOI because maybe you don't want, if there is a collision or an error, you don't want to go back, get a NAC and retransmit again. So maybe you transmit a several number of times. So this is the diversity sorted. And now, so this is also very, this is also fine in textbook. And now, you can introduce something new. And this is a work from 15 years ago from Cassini and others. So they assume and they introduce a mechanism which is to put inside every packet an indicator, a header, where the position of the packet are indicated. So, okay, I go back, maybe I didn't explain that here the user wants to transmit one packet, but it's sending exactly the same packet several times, 2 times, 3 times. So each user transmitting 2 times, and then header is indicated, okay, on which slot, which are selected by the user will transmit. If you do that, you can have, I give an example, you can construct a protocol. You can have, on this example, 5 nodes transmitting in 6 slots. So this is not, in the frequency domain, you can imagine it's only one channel, like in random access. And then each user has selected randomly some slots. So user 1 selects slot 2 and 6, and so on. So now the receiver sees something. It sees the superposition of all these transmissions. But what it can see is on some slots, there are only one transmission, so we can use a normal decoder and recover packet. There is slot 2 and 3, and on other slots, it's like in classical random access, there is a collision, so it cannot recover packet. And then you can use this trick of inter-slot successive cancellation, so get the packet, reconstruct the channel, and remove on the slot where you know it is repeated. And this is, you know where it is repeated because of the header. So you can remove the packet, and then if you do that on this example, what happens is, okay, you remove some of the packet that you have decoded, you have new packet, new user that you can now decode, and then it's very nice because you can iterate this mechanism, and in this example, you decode everything. It's not always the case, but it's a principle. So of course, there are some physical layer detail, like how do you conceive the system. So in this article, the author proposed a full model. They didn't implement it, but I will show some elements. So, okay, you have a normal modulation, like you have a preamble, it's QP is QB. Okay, compared to an ideal system, like I show first, where you can always remove or do a successive interconnection constellation inter-slot, you don't have much difference if you have a system where you can have estimation error, at least in their setting. So they have figures, they have some graph of, for instance, here, it's a distribution of the phase error of the amplitude estimation, but in their settings, everything works fine. And now I want to mention that actually CRDSA has been part for some time of DVB, the satellite communication standard. Now that's the main idea and how you can use it. Now there's a question before, in the previous work, packets are repeated 2 times. But why should you repeat them 2 times? And also, how do you estimate the performance? So what a similar work has been done by Lever. He took back the assumption that the number of transmissions are fixed. Instead, what he did, he assumed that the transmissions are taken from a description. So a user can decide to transmit twice, 3 times, 4 times with some probability. So this is what is called the degree distribution. Let's say maybe half of the time it transmits 2 times, half of the time 3 times. And he still use a ideal channel model, even though he did also some simulation. And the key point is, if you look at this system, actually you can see a very strong analogy with the decoding of LDPC code for a binary erasure channel. So what it is okay, try to formalize the decoding process. So you have user here instead of a variable, and then your slots they are similar to parity check nodes, and then you can model the decoding process exactly like LDPC decoding, and you can use the tools of LDPC decoding. So you will in LDPC decoding, I will not go into details, but you will model the iterative decoding by iterative equation. So the equation, more precisely the state of your decoding, is represented implicitly by 2 quantities. After you recover user, how many users you have recovered, more or less, and after you do see how many slots are free. But what is important is, okay, you can use the tool of coding theory, keep, basically you have recursive equation that you can iterate. But what they give you at the end is one tool where you give a probability distribution, and when you give a given load, like 0.5, and then you can compute the throughput that you will get. But of course, not of course, but you have to note that this throughput is through a shift for infinite or very large frame size. So once you have this tool, what you can do is then try to optimize, find the optimal probability distribution and load. This is what Lever did. He did it numerically. So he found, for instance, for up to 8 transmission a distribution. And if you look at the throughput versus load, you get a curve like this, a curve which is given by the tool of density evolution, and it goes up to 0.98. Of course, yeah. So of course, this is asymptotic, as I said, in the size of a frame. So now it's proven that you will reach with a sufficient frame size from the LDPC theory. But if you do simulation like with 200 slots, you get a little less, or more or less less. So here you will get up to 0.75 or a little more. So 75% of throughput. So this is very good. And this is maybe what generated a lot of interest and excitement. And there's a sub-literature about this. And this is maybe why it has been called modern random access. So now, yes, there's a question of how far you can go. There have been, shortly after, there have been a work that's just okay, you can use the solitone distribution in this case as well as it was used in LDPC code. And then asymptotically, you can reach 1 packet. So you have achieved maybe the goal of people doing random access. You can use all your slots successfully. So now, of course, there's a large literature about that, and there have been many variants. So I was lucky to be able to work with many people here. We work on variant like, of course, where you have power imbalance. So you're doing inter-source of normal SIG, normal NOMA, normal power domain NOMA, as well as IRSA. And then, okay, we didn't introduce it, but we found some different results. So one of them is, for instance, this result, where we try to see what is the performance of this technique. So I don't know if I gave the acronym, but it's IRSA, Irregular Repetition Slotted Array. So I will use this name in the rest of the presentation. You can get the throughput when you do IRSA with 2 power level up to 1.7 packet per slot. So you get more than 1 packet per slot because you are doing power number. So this is very interesting. But there's no, in this case, there's no tool that gives you exactly, or you don't know what is the optimal distribution in the same way that you know what is optimal distribution for normal IRSA, which is held by the solid. We don't know. So there are some bound and some empirically found distribution are close to. Okay, so you can play a lot with variants, like what if you introduce the capability of receive several packets at the same time and so on. We have been working on that. We have results. It's interesting. So you add diversity and the main feature when you are adding such diversity is that you can increase your packet load rate when you have low load. So these techniques are very interesting. There have been people even in IC Bangalore, so I don't mention, but we have been involved in the CEFIPRA project also, and we have worked partially on this subject in this context. And then people have been integrating this technique inside normal NOMA consideration or NOMA settings. Okay, so now I will present some direction we are interested to study, which is, can we go towards more realistic IRSA? Because in what I presented, there is an ideal collision model. So what I think could be interesting is to have what I call in this slide a receiver-only IRSA. So you take a normal ASIC, which has been implemented. You don't want to redesign the modulation, whatever. You take just ASIC, and then you think, can you do IRSA with that? So it can be done. You just need to modify the classical receiver. Of course, you will have some detail to change, but it will be mostly in the logic, so it could be in the firmware, like how do you send pilots, how to manage the HIRQ and so on. You should probably remove it. And then you have a classical transmitter, and then of course you can use it a classical receiver when there is single transmission. You recover a signal from A, for instance. And the difficulty you have is, of course, in the implementation of this inter-slot SIC. So you have your classical transmitter, you get super signal, and you need to estimate the parameter to remove the copy here and to feed it back to the classical receiver. So this is one thing we are studying. Also now we don't want to assume that inter-slot SIC is perfect. So there have been some work also with people in Nokia where there was an assumption that the inter-slot SIC, decoding, the inter-slot SIC will fail with a fixed failure probability. For instance, here, in some of the work, we assume, let's say, every time we do SIC, we fail with probability 0.1. So there are some results, but that doesn't tell you what is the performance in reality. So currently there is some work, including with Said, in this room, to go back to this receiver only and to try to at least evaluate it through simulation. So we take normal tools we generate based on signal, like 5G signal with 5G sanctional code, modulation, everything, OFDM, of course, and we look at what is the performance. So these are curves that Said computed for yesterday. And then we can see that at least in some settings, you have a very small difference, which is also confirmed by the previous work, but we don't know how far you can go. So now you can look at what happens if you have lot and lot of superposed signal. So you have to remove lot and lot of them. Every time you do a removal, you have an error and you leave some energy on the slot that had a little bit. And then you can see that after doing that, here it's an evaluation of the probability that there is an error in decoding, and here it's the number of removal. So when the number of removal increase, you can see that probability of error is 1 or a little bit above that. So this was done yesterday. And then this is an issue because when you look at the soliton distribution, for instance, you can reach high throughput only if you have a high rate. Not only the soliton distribution, but in general, the capacity, the throughput of ear cells is linked to the number of transmission, and it has to increase to get close to 1 packet per second. And there is this question of, okay, what is the best, or how to improve the intercept technique? We did some experiments a long time ago on a testbed. I was escaped and late. And then this is what we want to do with this kind of work towards realistic ERSA with let's say receiver only, so more realistic model, study the impact of residual error, do some real experimentation or simulation with more and more realistic channel. So I have the last part. I don't know if you have much time, but we are sort of in the DRL session. So this was the link between MAC layer and a physical layer. Here we did some work in the context of, for instance, the thesis of Iman and Dush to improve just the MAC layer. So again, in ERSA you have to select slots. You are selected randomly after you select a degree, number of repetition. Now, as Marceau and Naresh have presented, you can use deep reinforcement learning, optimize your system. It's good because you can adapt to many variations of your model, or your system model. I will just briefly keep to one main result. So what we did with DRL is have one model, the same model for everyone, which decide on which slot the transmission has to be made. And then it has to be to generate random code, because if the model is sending exactly the same thing to is selecting exactly the same slot for every user, there will be collision, obviously. So maybe the model for free user select some slot for user 1, some slot for user 2, some slot for user 3. And then in this case, you can see that there is a double collision, so you can decode only one user. You can use PPO. It's a short episode. Of course, there's this question of how do you design the rewards function. So we just take a rewards function is objective function, so it can, maybe it's not good, but it cannot be wrong. We spend a lot of time on that. And then we run the training. And then we saw that, okay, the convergence was relatively quickly. So it's a little bit surprising because the space, the action space is huge, but it's helped by the fact that we have a policy method which is stochastic. So we select the output of a network is the probability to select one slot. So anyway, here there are 25 users, 25 slots. We reach 12, which is roughly what you can expect to have at best. I keep that, and I will probably just mention that we added more feature like adding a sensing phase. So the idea of adding a sensing phase is somehow to model abstractly what you could have in a relay system if you take into account partial observation that you have on some event or some feedback from the base station. Anyway, there's an interaction phase, and I just want to mention that, okay, user interacts, so they take decision to send burst or not, and you can apply DRL, and it's more complicated because your action space is not only a single decision that you take for one time per user, you have to take several decisions. And it works only for a limited number of users. So I think at least this technique is a good benchmark for doing sophisticated protocol, and actually protocol how to interact, which decision we can take to interact using the past observability of events. And I will conclude by this. So, okay, this is an overview of modern random access, and the work is in twofold, trying to make it practical, trying to compute the actual performance, trying to improve, or even when you have small size, the density evaluation doesn't give you rest. Maybe we need to go back to the LDPC shortcode director. Yes, this exciting journey.
Long live India and France friendship.